Hi, this is Mr. Sid again. I'm going to show you, I made this little worksheet on ion configurations, and really this is where charges come from. And so if I say, let's write out the noble gas configurations for all these, and these should all be in the same period. So I got sodium, magnesium, going all the way across to chlorine. Okay, so sodium, they all start with an inner configuration of neon. Those are your core electrons. Okay, now let's add the valence electrons. For sodium, I add a 3s1. For magnesium, 3s2. Now the rest of them all have that same 3s2. Okay, and now as I start to go across from aluminum, you start to add the 3p's. So aluminum would be 3p1, silicon is 3p2, phosphorus is 3p3, sulfur is 3p4, and chlorine is 3p5. Now you see each one is in a different period. So every alkali ends in an S1. Every alkali earth is an S2. The aluminum family, they all have the S2P1. Go to chlorine, they all are S2P5. Okay, now, going to the right, what I do is I say, what's their common charge? Well, sodium's a metal, and it loses a 3s1, so it's a +1. So it loses a 3s1. Its noble gas configuration, that of neon. Magnesium loses the 2s, and it just becomes neon, because the atoms are leaving. Aluminum becomes +3. It loses these two +1. Its configuration is just neon. Sodium, magnesium, and aluminum all have the configuration of aluminum. Which one's the smallest of the three? Aluminum, because it has the most protons. Okay, it has the most Z effective, if I go back to Z effective. These all have the same number of electrons, and our term for that is iso, which means the same, electric. To be isoelectronic or isoelectric means you have the same number of valence electrons. Now as soon as I go to silicon, I've crossed the Zinel line, and now I'm not losing electrons, now I'm gaining electrons. My affinity kicks in. The ionization energy starts to increase, your affinity starts to increase, so instead of losing electrons, you're now gaining electrons. So silicon, it has 2 in the P, and if I was to look at the configuration up there, it has 2, it has room for 4 electrons, so it becomes a -4. And its configuration becomes neon with 3s2 and 3p6, which is isoelectric with argon. It takes on a noble gas configuration because it's filling them up. Phosphorus only needs 1, 2, 3. 1, 2, 3. So phosphorus configuration becomes neon, 3s2, 3p6. 3 plus 3 makes 6. It also has argon's configuration, but it's not argon. Okay, it's phosphorus with a -3 charge. Okay, but that's why it's stable. Their shells are full and it has a high affinity, so it tends to be stable. Sulfur has room for 2, it's P4. So sulfur becomes neon. And I'm going to add a -2. So you know, if you're going to do a configuration, that if it's negative, you add electrons, and if it's positive, you remove the valence electrons. So I get 3s2, it was 3p4, add 2 to that, 3p6. It's just like argon. and that's a -2 charge. Any alkali has a P5, so it gains 1 electron to go to 3s2 and 3p6. Same configuration of argon and a -2. And that's how configurations are related to ions. We're either losing our valence electrons, that's metals, or we're gaining valence electrons, that's nonmetals. A terrible term that chemistry teachers like to say is, oh, they all want to be like noble gases. Well, atoms don't have desires. Metals have low ionization energy, so they tend to lose their outer electrons. Once that noble gas configuration is in place, that next electron has a high ionization energy, so they only lose the outers, not the inners. So they do end up with a noble gas configuration. Nonmetals tend to gain electrons to fill their shell because they have a high affinity, a high electronegativity. And they have a place to put it, so they tend to take on noble gas configurations. But in fact, they don't really want to get noble gas configurations, they just happen to get them. Okay, now I put a couple of transition metals on here, just for thought. We look at what's going on with zinc. Zinc has 30 electrons. Its core is argon. Then we come in with the 4s2 and a 3d10. Now, what charge does it pick up? Well, it's going to lose the most outer electrons. This is your lowest affinity to take away the 4s2. So zinc becomes a +2 charge. It loses these 2 outer electrons. So it's a new configuration, becomes everything that argon has with a 3d10. You could write that 4s0, but it's gone. Okay, so that's the outers that are lost. Let's do iron. Iron is argon with a 4s2 and a 3d6. 1, 2, 3, 4, 5, 6, 3d6. If I wrote this as a config, 2 electrons in that s, and then 1, 2, 3, 4, 5, and then 6. Okay, now what charge? I put the charges in. Iron tends to take a +2 charge as its first charge. It's losing the most outer electrons from the 4s2. So iron with the +2's configuration is argon with the 3d6. Now iron will also take a +3 charge. The reason it takes that +3 charge is these 2 electrons in that d orbital repel. So that 1 electron has a very low ionization energy, and it ends up getting a configuration where all the orbitals have 1 electron in them. And that's its most stable configuration. It's Fe +2, 3, equals everything that argon has with the 3d, 5. And when we look at that, we go, oh, that's the stability of the half filled. And anything with spinning electrons that would be magnetic. Okay, tin is down here. One of your problems is usually finding these atoms. So usually when I give you a test or a review, I'll put all the atomic numbers on them so you can find them quickly. Okay, tin is everything that krypton has. Okay, and then we get 4 down here, 5s2, 3d10, sorry, 4d10, 4d10, and then 1, 2, 5p2. So what's a +2 charge for tin? Well, in a +2 charge, the first thing you lose, the most outer, is the p. So that p is going to be lost first. So it has a configuration, Sn +2 is 5s2, 4d10, and your 5p2 is gone. If you get a +4, you're losing those 5s and these S's. So tin with a +4 is losing that 5s too. And I should have krypton in there. So it's everything that krypton has with a 4d10. If I looked at tin in that configuration, it shouldn't be magnetic because all the electrons are paired off. That's called diamagnetic. Something like iron, where they're all in one direction, that's called paramagnetic. And para kind of means like extreme, when you have like a paramilitary organization. I think I'm going to shut this down and I'll finish the rest real quick because I don't want it to be a long file.